In this video, I'd like to discuss what the free means in Gibbs free energy. And it turns out it's more like free speech than free beer. So we're not giving away energy, or we're not giving away beer for no cost at all. We basically are allowed to talk. We're allowed to use the energy. So here's a chemical equation. So let's take some graphite and react it with hydrogen to make methane. And we can calculate delta H of reaction, so we can use the heats of formation, and we can look up the heats of formation for products and subtract from reactants, and we'll get minus 74.6 kilojoules. So one way to interpret this is that for every mole of graphite reacts with 2 moles of hydrogen to make a mole of methane, we release 74.6 kilojoules of heat under conditions of constant pressure. So it's an exothermic reaction. And you might say, well, maybe we can use that heat, right? Maybe we can use that 74.6 kilojoules every time we make a mole of methane to do stuff with. Hold on. So it turns out that energy is not free to use, so you can't use all that heat. So we have to go ahead and we calculate delta S of reaction, and delta S of reaction is minus 80.8 joules per Kelvin. So that immediately tells us that the reaction itself, the molecules of methane, have fewer microstates than the molecules of hydrogen and graphite. If you like, the methane is more organized, the reactants are more disorganized. So we have to pay the second law tax. We have to increase the entropy of the universe. So we can't just use all that heat to do whatever we like. We've got to use some of it to pay the universe's tax. So we calculate delta G of reaction, and as assigned to whether the reaction will go or not. And at 25 degrees C, you should be able to calculate this is minus 50.5 kilojoules. So that tells us a couple of things. So one, it tells us that it's spontaneous. It's a green light to the reaction. But the second thing that it tells us is that we are free to use this much of the energy to do work. So we can use exactly this much energy to do work. So the heat that's given off, although we're giving off 74.6 kilojoules, at most we can actually take 50.5 kilojoules of that heat and turn it into work. So if this is a powering an engine or something, we can use that much heat to do the work. The remaining 24.1 kilojoules, the difference between here and here, we've got to release to the surroundings in order to balance out the entropy of the universe, in order to increase the entropy of the universe. So we're welcome to use none of it at all, right? I mean, we can waste the money, we can waste the energy. So when this reaction gives off 74.6 kilojoules of heat, we can just let it go ahead and give off that heat and increase the energy of the universe. So we can go ahead and calculate delta G minus 50.5 kilojoules. But we can also take that heat given off by the reaction and use some of it to do work. So we can actually use 50.5 kilojoules to do work. So we can convert the heat into work, but we can't convert all of it. So we have to actually dump out the remaining 24.1 kilojoules as heat. And that ends up giving us, at the end of the day, delta G is 0. So all our free energy is expended. We don't have any left. So it gives us the maximum amount of useful work we can get out of a system. So we can't use any more heat than this.